Hello all, my name is Afonso Oliveira. I'm a software engineer at Synopsys RISC-V team, and I'm also a key contributor at the RISC-V Unified Database project. And today I'm here to show you how we can use this RISC-V Unified Database project to automate the RISC-V extensions porting to Binutils, to QEMU, and to all the other downstream tools. So, today we will cover the challenges with the RISC-V ecosystem to kind of understand where does UDB come from. Then we'll see what is the RISC-V Unified Database, and then we'll see how we can use Unified Database for tool development. We'll show a Binutils use case and also a QEMU use case. And well, lastly, I'll do a little call for adoption. So, starting off with the challenges with the RISC-V specification, I really want you guys to think about this as growth challenges with RISC-V, and I hope I can convince you of those by the end of this section. So, starting, RISC-V has several disconnected specifications or manuals that describe the specification. The main ones are obviously the ISA manual, which I suppose everyone's already found and used, but there's also the assembly manual that describes the pseudo instructions. There's RISC-V opcodes that is used as a machine-readable database until now for RISC-V instructions. A lot of the vector extension is described over there. And there's SAIL, and SAIL is a formal specification of the RISC-V model. But in reality, these are just 4. And if you're really developing in RISC-V, you'll come across many more of these repos. So some of them are peripherals, but in reality, some of them actually also touch the ISA, and for you to actually develop any software for RISC-V, you'll find yourself trying to figure out what's going on in all these different manuals. And, well, I also did for quite a long time, and it was not a very easy process. And while I was trying, there was a point in which I felt I could not at all, and I was very confused. But, well, eventually it got slightly better, but still, it was clear to me that this approach was not ideal. And so, I decided to investigate. Why is it like this? And starting by the ISA manual, which is the manual that's the main manual, I would say, we can see that the ISA manual is totally written in ASCII-Doc, which is kind of an evolution of LaTeX, and it only generates either ASCII-Doc or PDF, which is not ideal, and you also have other challenges, like how can you verify the ASCII-Doc? Very hard. Then you'll have, how can you diversify? How can you create manuals from that manual? Will you copy-paste it? Well, it's kind of the only option with the current state. And, well, I told you there is a machine-readable source, for instructions at least, but even this... Yes?
What do you mean with verified?
So, the ISA is composed of instructions, CSRs, and this information resides in multiple places, right? So I showed you different manuals. So how can you verify that all of them are coherent with each other if it's just text? In the ISA manual, it's not a big problem because there's thousands of very smart people reading it and writing it, and eventually this iteration will solve it. But when you go into diversification, there won't be 1,000 people reading your downstream manual. So this approach won't allow you to verify it downstream. And even upstream, we do find those little bugs here and there. Yeah, but so, moving on to the RISC-V opcodes, this is a more verifiable one. It's machine-readable, but I really tried to encapsulate all the RISC-V specification here. I tried to submit some patches, and I eventually got to the conclusion that it doesn't allow all pseudo instructions. So you'll never be able to overcome that the format doesn't allow it. It's not possible. And it also doesn't allow you to specify your implementation-specific mirrors there. And how many tests can you run on that simplistic format? You may run some, but you definitely won't be able to test everything we would like to test. And so, clearly, the RISC-V ecosystem is not bad at all. That's why we're here today, and a lot of people are developing on RISC-V. So why is this? And I looked like, what happens so that we end up in this state? And the reality is it was first published, the manual, in 2015, and it had 5 extensions. Today, it has more than 200, if you count with profiles and so on. And it really is a big difference for the same infrastructure. And RISC-V opcodes kind of around the same problem. You may see a first commit here from Andrew Waterman. It was in 2010, 5 years prior to the first release of the manual. And it was refactored, but some previous problems stayed. And it also went from 5 to 200 extensions. There's no way around it. So in reality, what I think this is an infrastructure problem within RISC-V specification. It was outgrown. And so, as a quick summary, the information exists in disconnected repositories and sometimes is very hard to find. Sources are sometimes not official, like the assembly manual, RISC-V opcodes. These are not ratified. These are people, very smart people that maintain them and keep them in shape. But there's no official organism that checks if it's really correct. And the data ends up being sometimes not reliable and have very, very small inconsistencies that, although may seem harmless, these small inconsistencies can translate into hardware bugs and things that we definitely don't want. And sources of truth can't really encapsulate all the information as it is. There's no way of getting around this. And when I got to this conclusion, I very well thought, well, there are sources of truth because, well, I compile my code and then I run it, so everyone has to have this figured out, right? And I thought, well, this has to be the tools. The tools guys have figured this somehow. And I started digging. What tools have this information, these instructions, these CSRs? And a lot of them have. So the kernel has it, QEMU has it, Gem5 has it, GDB, the GNU toolchain, has all of this information. Golang also has this information. And again, this is all in their sources. Zephyr has all this information. This, I guess this compiler is not for today. And so this information exists in all these different tools. And if we look to the left, we realize, okay, so it's very hard to find this information and people struggle to go around all these repos. And in the other hand, this information exists in so many places. So what does this mean? Well, a lot of people have struggled very hard, and then they've encapsulated it on their own project. But when a new project comes along or a new extension comes along, everyone will have to go back to the first step, figure it all out, and then go to that tool and update their tool. And this is happening in like 100 different tools, 200 different tools. This is definitely not ideal. So the idea here is, well, what if instead of all these things in the left, we could kind of put this information in a central place, get it through some layer that actually makes it machine readable and not to keep all that ASCII token and formatted text. And then all the tools may consume it in a structured way that comes from the single source. And this is what the UDB is all about. So, moving on to the RISC-V Unified Database, I want you guys to think about the Unified Database as two different things: a single source of truth and a tool that generates several outputs. These are kind of separate, but exist in the same repository. So, let's go over it. First, this is what the unified database looks like from a high-level view. You have your golden source of truth, your tools, and your use cases. I won't really go over the tools today because we don't have that much time and you guys already waited 15 minutes for me to start. But we have the golden source of truth. And let's see what golden source of truth do we have and what do we encapsulate there. So we do encapsulate instructions, CSRs, profiles, architectural parameters. I won't go over all this today, but let's focus specifically on instructions. I'm pretty sure all of you guys here know what instructions are, the normal operations that your processor executes. And so the UDB encapsulates all its information in a YAML and a bunch of YAML files that are very organized and follow a straight schema. So for instructions, the main parts that we have to go through are the name, the long name, descriptions, what extensions define each instruction, its encoding, access mode, and even formal specification, so the semantics of it. So if you look at the right, and we go from the top to down, you'll see that all this information is there. So this is an app, it's a very simple one, but you may see that you can see the extension that defines it. In this case, it's the base ISA, so it's I extension. You have your assembly fields there. You have encoding, which has your match, your fixed bits, and your variables there. In terms of variables, this is our first schema for variables, but it's evolving to also possibly encapsulate relocation information. And from there, we can use it for more downstream use cases. But that's an ongoing discussion. If anyone of you is interested in that, please join that discussion or talk to me after this talk. And well, then we have semantics. So there is actually two formal languages here that can describe your spec. I won't go over the details between one and the other, but there are semantics inside the unified database, and you'll see what we can use them for later in this presentation. So, what do I believe we can build with this? I believe the UDB is not just about the tools, as I told you, but it can encapsulate the documentation, so your ISA manual, your PRMs, TRMs. It can also be used for certification. So for you to write architectural tests, you can base yourself in the UDB data and actually ensure that every CPU that says it has implemented what it has really has that implementation on it. And you can use it for tools, obviously, and that's what I'm going to go over today, and it as the main purpose of this talk. And you can also use it for AI agents, but let's not go too much into that here. So how can we use UDB for tool development? Today I'm going to go through two use cases. One is a proof of concept of how we can use UDB to generate Binutils for new and custom extensions. And the other one is UDB to QEMU, and well, when we get to it, I'll explain what was done there. So, UDB to Binutils. Actually, I do have a reason why I chose Binutils to demonstrate here today. And the reason is, we at Synopsys at RISC-V, we have a lot of DSP extensions, and those have lots of instructions. And once I had figured kind of the background of this talk, I was like, well, if we do have so many instructions, and these are custom ones, so I kind of know the guys that are doing this, and I know where they're doing it. So are they suffering the way that I think they're suffering? And the answer is yes. This is 4,200 lines of declarative code that I found in a single commit that someone had to do to describe the DSP extensions. And I believe that all you guys agree with me here that is poor guy, right? We don't really want to do this. And so I thought, well, I think I have a better way that I can help people do this. So I started. And as a goal for my approach, what I wanted to do was mostly an aid to developers and, well, to ensure that no one will lose their eyesight after writing those 4,000 lines. But what I don't try to achieve here is full replication of Binutils. We're not trying to full match what's already there. We're just trying to allow people to save a lot of time in this porting of new extensions and to avoid them spending a week writing 4,200 lines of declarative code. And even make that process more standardized, so it's not handwritten, it's based on a source of truth that's already verified and that you can trust. And so, what do we do? So, quick disclaimer here, I'm not very familiar with the toolchain, I'm not a toolchain engineer, so if I do say something that's not 100% correct, please be easy on me. But what we generate with this is, so as I believe Binutils, the main file for instruction description here, is the RISC-V opcode .c, and there you may see the description of an AND, and this is our example, so it has its name, its class, its operands, match and mask. Well, this is a standard definition, and then pinfo, that 0 over there just means that this is an instruction and not an alias or a macro. So as you've seen in our YAML definition, we have all this information, so we just have to make it work, right? And well, then there's other files, so there's a definition of the masks and the matches inside Binutils as well, and we can also generate tests, so I based myself on a couple tests I found, and well, obviously all the tests are tests that pass and that fail, there's no third option, but I'll show you how I achieved these tests. So in the RISC-V opcodes.c, this is an example for the I extension, the base ISA, so as you may see, we successfully converted all the data in UDB into the Binutils format I showed you before. And if you check the branch equal here, there is a warning that, well, to find operands, I'm basing myself on the operands that already exist. I'm not trying to make up definitions in the Binutils. So when we find one that doesn't exist, we'll warn you that you'll have to define this by hand. In this case, obviously, this one existed inside Binutils. This is more than ported into Binutils, but it's my example of what you may find if the operands don't exist. And so this is the definitions in the RISC-V opcodes.h. These are the matches, the masks, and the declaratives of each instruction. And the tests, so here on the left, you may see, so these are all incorrect ways of describing an add. So with only one operand, it takes 3. With 4, it's also not possible, or with wrong types. So here, these are immediate fields in fields that are registers, right? And to the left, you'll see just a normal add instruction that should pass the test and should not and should be successfully assembled. So my call for help here to you guys is, I believe in this room, most of you should be toolchain engineers. And we do face a problem in all these downstream tools, which is kind of a chicken and egg problem, which is, I may start these tools, but I'll never get them perfect without the review from the people that will actually use them and port them into Binutils. So review and feedback on these tools, and even help to kind of get all the intricacies of downstream tools, either it is Binutils or other tools that you may have a use case for. This iteration is very well needed. And well, I have a proof of concept here. If you guys want to go over it and kind of enhance it or help me understand what we need to do to enhance it, I'm all for it. Please approach me. And yeah, we need iteration. We need to drive adoption within the community to have this more standardized way for all the tools, not just for Binutils. And we kind of have some resources to do this. There's mentees working on this from RISC-V mentorship, and they are actively working in this project. So please talk to me, and let's see how we can make this all work. And so this was the Binutils approach. Now let's go on to QEMU. So this was also actually not done by me. This was presented in the KVM forum earlier this year. And this was done by rev.ng labs. All their code is open source on these links. And this was done by Anthony Johansson and Alessandro Di Federico, if my Italian allows me. So what they did was they tried to achieve an emulator in the loop extension design. So they were helping Qualcomm write an extension in UDP and then quickly emulating that extension in QEMU, so that you could rapid prototype, actually understand what works and what doesn't work. You can have a cross-version validation between your extensions if you're writing extensions, and you have immediate toolchain testing because of how QEMU works. So their pipeline so for this they used IDL for semantics, that language I showed you before, and they were able to get it down to tiny code generators on QEMU. And well, I won't go over the specifics of their implementation, but if you're interested, please look at the link. Now, other use cases that we can use UDP for. So UDP is being used by the certification and steering committee from RISC-V to create architectural tests to actually get, so I believe that in the next period, in the next months, you'll actually need to use UDP to call your processor RISC-V and actually go through the certification process that they're coming with. Qualcomm created an extension, an instruction set simulator integrated with Renode from those semantics as well. We at Synopsys are using UDP as a central point, so we're creating an ARC-V programmer's reference manual out of it. We're creating other tools, as you saw, the Binutils tools. And I believe all downstream use cases of RISC-V opcodes, if you do have them, can use UDP, and you can replace RISC-V opcodes with UDP information. So as for community endorsement, UDP is currently being developed by different companies. At some point, this was almost just me and Derek from Qualcomm, but now there's way more people working on this. We have 13 RISC-V mentees working in UDP, and there's 5 that are still working. We are an official SIG under RISC-V organization. And please join us if you want, if you have a downstream tool, or if you actually want to help us create UDP schemas and so on that will fit your interests. Join us, check our GitHub. Our weekly meetings are linked in this presentation, or contact me either by email or here at the conference. And thank you, guys. If you have any questions.
So thank you for introduction of the problem, but so what happens in the sense of addition of new extensions? So how it is going to be related to UDP? Is there any enforcement of like not introducing more to that problem with new extensions and population of all of these separate tools? So how it is going to be related to UDP? Can we somehow use that?
Yes, so there's kind of 2 ways of looking at this. We can port new extensions into UDP, and then we'll have a source for all the tools. Or, as some working groups are doing, I believe AME matrix group is working and is creating their extension directly in UDB. And from that, they'll be able to generate their document for the ISO manual that they'll need to ratify, but they will also be able to have this downstream, so they'll be able to do this porting to all the new tools from their original design in UDB. Does that answer the
It was more on so these are like voluntary done activities, but maybe there is some point of trying to make it as a standard way of getting information about new instructions, extensions, and CSRs, because then you have that automatic alignment.
Yes, so we were for a long time trying to generate the ISO manual out of here exactly because of that, but we kind of realized the ISO manual is not going anywhere, at least for now, and the way it's written, it's staying. And so we shifted towards generating the RISC-V Programmer's Reference Manual, and that's already in the UDB repo. It's kind of the goal for the NA Summit to kind of get people into using the programmer reference manual if they actually need RISC-V information other than just going to the ISO manual, as it has an index of instructions, an index of CSRs, and it's somewhat more complete than just the ISO manual. Thank you. Do we have any other?
So you're saying that the ISA itself is not moving to UDB soon?
Well, to move the ISA to the UDB, we need to convince everyone to move to UDB. And that, in RISC-V terms, means a long time of convincing people. So instead of moving what already exists, and although I've pointed a lot of flaws, it works. People are building CPUs out of there. We're using it for something that doesn't yet exist and is very well needed inside RISC-V. So we're getting and convincing extension authors to use UDB instead of being just for the ISO manual to actually have a programmer's reference manual where they'll be able to list all their instructions and so on, that many of things extensions in the RISC-V manual don't use. Thanks. Any other? Or this is it and we're all going to have lunch? I guess you guys are hungry, right? Okay, thank you guys.